So this is what we're doing. We're trying to use superposition to find the IT. The first thing that we did was to draw a table. We're going to leave only sine 2t on. So to do that, we withdrew the circuit, switched off the sine 10t, and left only the sine 2t. So after doing that, we changed these, the capacitance, the inductor, we're changing them to phasor, and this is the conversion, Z1 for the inductor, Z2 for the capacitor. Now, the challenge that we're having here was we also have to do the same thing for the source. We need to present it also in phasor form. So since we're given this, if you don't recall how they're supposed to be transformed, you can go back to the basics and use the double angle identities. So if you have cos 2t, what must you add to it? Z1 and Z2. So Z1, this is the inductance for the impedance for the inductor. And to calculate impedance for an inductor, we multiply the complex variable J with the angular frequency times the inductance. So angular frequency comes from the source, that's 2 in this case, 2 rads per second. Then the inductance comes from the problem itself, so that is a 1. So we're going to have 2 times 1, which gives us J2. Inductance is the same as resistance, so it will have the units of the ohm. Not say the same, similar. In the same way, to calculate the inductance for a capacitor, the formula is now 1 over J omega C, where C is the capacitance. So omega still comes from the equation, from the source, which is 2 rads per second. The capacitance comes from the capacitance there, from the capacitor itself, which is 1. When you multiply, you have 1 over J2. Now, if you wanted to get rid of the complex variable from the denominator, you have to rationalize that denominator, multiply the numerator and the denominator by J. So now you have J times J, which should give you J squared. But remember, J is root of -1. So when you square it, you just get -1. This is how in the denominator you remain with -2. In the numerator, you have 1 times J, which will give you just J. So the negative will be the sign for the whole term now. And then 2 into 1 will give you negative 0.5. 2 into 1 will give you 0.5. Then you have negative already there. It's something that you can always take. When calculating the impedance for a capacitor, this is the formula. But when the J goes in the numerator, the sign always changes to minus. So you can also remember it this way. Are we okay on the impedance?
Yes, so if you multiply, you have J over 2J squared. J squared is -1. That means that you have -2, and then -1 over 2J, which is -J 0.5 ohm.
Yes. Okay. Now we want to convert sine 2t. So that we write it in terms of cos. So how are we going to do it? To write it in terms of cos, want to find an angle.
Let me just see the circuit. You know, the bottom. No, the other one. Down. Yes. That is the superposed one, the converted one, right?
Yes, the converted one. We have shorted the other source.
Then the sine times sine 2TV as well.
No, it's the one we want to convert. We want to write it in phasor form. So, want to find an angle phi such that when we add it to 2t and take cosine of that, it will have the same meaning as the sine 2t. So from the double angle identity for cosine, we know this is cos 2t cos phi minus sine 2t sine phi. Since we want the expression to reduce to only sine 2t, it means that the first part must be 0. For the first part to be 0, it means that cos phi has to be equals to 0. And since we want the second part to remain positive sine 2t, it follows that sine phi must give us -1, so that the overall answer here should only be positive sine 2t. So the only angle that allows sine of it to give us -1 is 270. So phi has to be equals to 270, or 270 can be viewed as -90 degrees. Have you seen that?
This one, the cos 2t plus phi change to cos 2t cos phi minus sine 2t sine phi.
Do you know this identity?
Yes, cos a cos.
Yes.
Cos a cos. So now on this one, you have to change it in terms of the phasor for cos 2t plus phi. That means that one has to be zero, the other one has to be negative. And the only one that can be the negative. So if the negative can do the negative, then you get a positive.
Yeah.
Oh,
So,
270
so this means that sine 2t is the same as just cos 2t minus 90. So since we wanted to transform the sine 2t and present it in terms of cosine, we have achieved that. Vt in terms of cosine is now just cos 2t minus 90 volts. In an event that maybe we had some value here, maybe a 10, that would have been the peak voltage, would have also ended up having a 10 here. But in our current case, the coefficient of the sine is a 1, so meaning even here we'll have 1 cos and so on. Now, transforming it into phasor, if we're getting phasor polar from here, what do we need? You need the peak value. Remember the expression? We have V max or V peak cos angular frequency plus phase angle. So a phasor stores the peak value Vm and the phase shift. So in this case, the peak value is 1. The phase shift is -90. So this circuit now becomes 1 phase minus 90 volts. So that is our circuit now complete. So we have transformed our circuit into phasor form. Having transformed into phasor, we can now try to determine what I is. So to get what I is, completely up to you which method you want to use. You can use Kirchhoff's voltage law, you can use mesh analysis, you can use nodal analysis. Completely up to you here. Or you can even use classic total resistance, divide, and then get the current and so on. That can also work. So which method do you want to use? Mesh analysis, nodal analysis, or straight out total resistance and Ohm's law?
What would you use?
The voltage law. Okay, so if we're using Kirchhoff's voltage law, how would it work? Okay, so I want Ix. So I need to define a current that goes here. I can take this as maybe I1. I can take the current that goes there. I'll say that is I2. At this junction, I1 enters. They may not say small letters like that. We've changed everything to phasor, remember? So even our Ix, when we find it, we're finding it in phasor form. So let's take these as I1, the phasor branch current. So how is it going to go? So at that node on top there, we can have sum of currents is equals to 0. So I1 enters, Ix leaves, and I2 leaves, equals to 0. So that becomes our first equation. Then when we use Kirchhoff's voltage law, we have minus 1, phase minus 90, and then we have plus the impedance.
We've got the bar. The bar.
The bar. This is just a way of representing a phasor current. Since we can't have it bold here, it's the same as just saying current 1, current 2 here. And then here, remember they wrote Ix. This is Ix. Now I used the X bars and so and Y bars and so on, so that it's evident or it's clear. When we find Ix using this approach, it will not be the actual current we want. It will be the phasor current. Do you get my point? So I was just trying to make it different from the actual one. Because Ix we are looking for, it is a function of time, or it is in the time domain. But the one we'll find using this approach, it is the phasor current. It's its phasor version.
What about the currents, which are the I1 and the A?
These are defined. We've just defined them. They are not necessarily there. We're not interested in them. We have defined them. Since you chose that I use Kirchhoff's voltage law. In Kirchhoff's voltage law, I need to sum voltages around a closed loop, which is what I'm doing here. To sum a voltage around a closed loop, when I reach impedance or a resistor, the voltage there will be the current passing there times the resistance. So the current passing there, for example, for this resistor here, the current passing there will be the one I've defined as I2. And then the resistance will be 1 ohm. That is why I was forced to define them.
You're looking at the node.
Pardon?
You're looking at the node.
At the node, when I was doing the node, I was right here. I'm done with the node. Now I'm going to start looping.
The node was summation of current of IC, meaning I1 minus IV of X minus I2 is equal to 0.
Yes.
Because of that node there.
At node A, yes.
From there now you loop. We are using both Kirchhoff's current and voltage.
Yes. Is that right?
Yeah.
So I'm looping. I've started with the volt here, the voltage source. Now I'm going to Z1. For Z1, I need to multiply the current passing, which is I1, times the impedance there, which is J2. And then I reach the bottom one there. So I have plus the current passing there, Ix. Then I have the resistance there, or the impedance there, minus J 0.5. That's the last one in this loop. So this has to be equals to 0. This is in accordance to Kirchhoff's voltage law. We simplify this a little. So we have, say, plus J2 I1 minus J 0.5 Ix is equals to 0. We can move the other term to the right side. We now have J2 I1 minus J 0.5 Ix is equals to 1 base minus 90. We can hold on to this as the first equation. Now we move on to the second loop. Oh, remember we already had this one here, right? And from this one we had I bar 1 minus I bar x minus I bar 2 is equals to 0. So here we can say that I bar 1 is actually equal to I bar x plus I bar 2. Let's keep this as number 2. So now we can go to the second loop. When we go to the second loop, which is here, what do we have? For that loop, sum of everything there also has to be equals to 0. So when looping there, observe that now we're going the other way. We're going to be going against the flow of current there. So the drop there will have to be minus Ix, multiplying the impedance there, which is minus J 0.5. When we continue, we find the 1 ohm on top, same direction as I2, so we'll have plus I2. And then the resistance there is just 1. So this has to be equals to 0. Are we okay there? Okay, so let me use purely resistive. Suppose we're dealing with a DC circuit. Current going down means positive is on top, negative is down. Positive is here, negative is here, positive here, negative there. So when looping around, take for example this loop. This is Ix. Here you have I1. Here you have I2. So let's say this is 1 ohm. This is 2 ohms. And this is 0.5 ohms. So when using Kirchhoff's voltage law in loop 1, which is this one here. So first, you find this voltage source negative first. When you continue, you come to this source. You find the source positive first. So you have plus. Then the resistance times the current passing there. When you reach this resistor, you find it positive first. So you have plus the resistance 0.5 times the current passing there, Ix. So this is what will be equals to 0. But observe what happens when you loop this side in loop 2. For loop 2, when you do the same thing, when you come this side, you find it minus first. So you will have minus. The current passing there, Ix. The resistance there, 0.5. And then when you continue, you find this one positive first. So you have plus. The current passing there, I2. The resistance there, 1 is equals to 0. This is what we did, but just for the AC part. What makes this to be negative is the direction of current. Our loop the way we are looping, we are going clockwise. We're going like this. But the current we are using is opposite to our flow. We are going up.
So what current, like if it was I1 and I2, the currents that we put inside the loop, are they part of the law, like the equation?
Which currents? You're talking about mesh analysis now.
Oh, those are the ones. So this one is Kirchhoff's voltage and current. You just have to deal with the currents they give.
The branch currents, yes. I have to say, even if you were using mesh analysis, you would still arrive at the same conclusion.
Yeah. Okay, so we can go back with this.
Okay. So we ended up with this expression. So from here, the minus will make positive. Then plus, this will just be I2. We can actually get an expression for I2 here. And it will be minus J 0.5 Ix. So this would be the third equation. Usually you want to solve these using Cramer's rule, much more efficient. But this one seems like everything seems like they'll fall in place perfectly. Let's try substitution.
How did you get?
How did I get?
The third equation.
So this is where your previous question came in. I used the voltage law on this part. So I was looping this side. So when looping this side, I said you come this way. Since you are going opposite to Ix, you get negative Ix there. Times the impedance here. The impedance here also comes with a minus. So minus J 0.5. Then when you continue looping, here now you'll be going in the same direction with I2. So you have positive I2. Multiplying the resistance there, which is just 1 ohm. So this is how we came up with this expression here. Do you remember?
Yeah.
Okay. So I've got equation 1. So first I'll use equation 2. Equation 2 says I1 is Ix plus I2. So where there's I1, I'll put Ix plus I2. So now I have J2, I1 shows up. Minus J 0.5 Ix equals to 1 phasor minus 90. We'll simplify this a little bit. We now have J2 Ix, J2 I2. This remains. Next, Ix, these are like terms, they can subtract. So we get J 1.5 Ix bar plus J2 I bar 2. For me to say that they are like terms, I checked first, they must have the same current. Next, they must also both be complex. So that's how I ended up saying they're like terms. 2 into 1, yes. Okay, so we're now here. At this stage, we recall that we had equation 3, which connected I2 and Ix. So where there's I2 in our new equation, we'll substitute equation 3. Remember, our interest is only Ix. So that is why I am eliminating the other terms, leaving only ix. So where there's I2, we're putting this. So this part will remain the way it is. The negative will be minus here. J and j will be j squared. 2 and 0.5 will be 1. 2 and 0.5 will be 1. And then we'll still have the ix there. Are we okay there?
You get 2 in 1, you got that one.
After 2 in 1, I got this one. Now, in 4, I'm substituting 3.
Three, 4, the new.
3 in 4, yes. 4 is the new equation. Is that okay? Is that fine?
Yes.
So we simplify. J squared is -1, which will make the sign on the middle to be positive. So this will now remain just ix is equals to phasor minus 90. This is the expression that we now have. So how do we solve this equation? Well, there are a number of ways we can solve an equation involving complex numbers.
And how can one less than -90 be converted to the complex number?
It's already a complex number the way it is. You mean converting it to rectangular?
Mm-hmm. Yeah.
Okay, so we'll show you how those conversions go. So from here, if you wanted to convert, you said you wanted to convert this to rectangular. That can be done, but I'll show you how to do it. But to solve this, I'll actually want to convert the rectangular to polar instead. Because I'll factor out ix bar. What will remain is here it will only be 1. Here I'll remain with j 1.5. And then this will still be 1, phasor minus 90. So from there, we'll have ix is equals to 1 phasor minus 90 over 1 plus j 1.5. When you're dividing, it's usually best to express everything in polar. They simplify easily. But if you wanted to see how to convert the 1 phase minus 90 into rectangular. So I'll present it as, let's say you had V max and a phase angle phi. To convert it to rectangular, you have to view the max as the hypotenuse here. So the real part will be the x component. The imaginary part will be the y component. The phase angle will be here. So this is how you would have to view it. So to get x, notice that all you need is the V max cos the phase angle. To get y, all you need is V max, then sine the phase angle. In our current case, the real part will be 1 cos minus 90, which is 0. The imaginary part will be 1 sine minus 90, which is -1. So that is what you would have to do if you wanted to make that conversion. So this will actually reduce to just -j. But instead of doing this, for us, we'll choose to convert the denominator from rectangular to polar. So if I wanted to convert from rectangular to polar, we're still basically using this triangle. Now V max will be given by Pythagoras theorem, the two shorter sides squared. So x is 1 in this case, so 1 squared. Y is 1.5, so it will be 1.5 squared. So this is what we use to get that solution. So 1.5 squared, we get that plus 1, and then square root of our answer. We get 1.8. To get the angle, we're going to use tan inverse, opposite over adjacent. The opposite is 1.5, the y. Adjacent is 1. So we have 1.5 divided by 1, then tan inverse of that. We get 56.3. So our Ix can now be written as 1 minus 1 phase minus 90 over the peak. We got 1.8. The phase angle, we got 56.3. Now, when you're dividing in polar form, the magnitude can divide, meaning it will be 1 divided by 1.803. And this is giving us 0.5546. The angles we need to subtract. So we're subtracting minus 90 minus 56.3. So when we subtract those, we get minus 146.3. So this becomes our expression for Ix. Any questions there? Okay. So we have obtained Ix in polar form. So we can leave it like that. So this is in amps. So get our Ix. Remember, this is superpositioning. We've just got what Ix is, and we're dealing with this in phasor. So even as we find it, we can choose to keep it in phasor for now. So we can say we're doing this in phasor. So keep this as Ix, the phasor version. So keep it here. This is in amps. Now we're going to do the same thing, but when we have sin 10t on. So it might be best for us to actually also represent the sources in phasor, not have them in time form, but present the current in phasor. So instead of having sin 2t here, I'll put the phasor version, and the phasor version we had was 1 phase minus 90. So here I'll say this is 1 phase angle minus 90 watts when this was on. So in the same way, we sought to say that when we wanted to change this, this source to phasor, first we got it as a cosine function, and we saw we just added negative 90 for it to become cos. So we expect that even for this one, when we take it to cosine version, there's a high chance we just have to add minus 90 as well. You can do it step by step. You will still see that you arrive at the same expression. And taking it to phasor, we know this will just end up becoming peak is 1, and then phase minus 90 as well. So we see that in terms of representation, it reduces to the same expression. So that is what we're seeing. So even for this one, we'll write it as 1 phase minus 90. So even though they're reducing to the same voltage value, notice that the difference between them is their angular frequency. And what does angular frequency change? It changes the impedance for the inductor and the capacitor, because in the calculation for impedance, there is dependency on angular frequency, meaning that for this, we will have to recalculate the angular frequency, the impedance for the capacitor and for the inductor. So you have to calculate those one more time. So we'll go back. Remember, now we are working with the other source, meaning this is the one we are switching off, and we'll have to short it. And the other one here will have to be the one on. Polarity, it's positive on top, negative down. And we've changed it to polar already, and we saw this is 1 phase minus 90. But we need the impedance for the capacitor and for the inductor. For the inductor, we have J omega L. But for this one, the angular frequency is 10, remember. So this will be J times 10 times 1, giving us J10 ohms. For the second, yes, this is
J10.
the 10 is coming from the fact that we have 1 cos 10t minus 90. The angular frequency comes from here.
Yes, then for the
The one
inductance,
is here.
so you've got the omega from the voltage.
Yes. Then for the capacitor, the capacitance C comes from there. So this will be 1 over J times 10 times 1. So this will be J over, let me not bring J first, 1 over J10. Then remember, when J goes up, what do I introduce?
Negative.
So this becomes negative. Then 10 divides into 1 to give us 0.1. So I can view the inductor in terms of its impedance, J10. I can view the capacitor in terms of its impedance, minus J 0.1. So now we are done. So for this circuit again, we need to find Ix. So in the previous example, we used Kirchhoff's voltage law, and we saw how Ix came out. So this time around, we can try to use, which method do you want? Or we can use, let's try nodal analysis.
Yes.
Okay, so which one do you prefer, mesh or nodal? Nodal, okay. So let's use nodal analysis on this. So if you recall, when using nodal analysis, the first thing that you need to do is to choose a ground. So we're going to ground this circuit at the bottom here. Once it is grounded, we're going to choose this to be a node, let's say node A. We want to find the voltage at that node, let's say VA. Then we use that voltage to determine the current that is passing here. Secondly, at this point, the voltage can be taken as whatever this source is supplying at this node here. So if this was VB, the voltage here is the same as what this source is supplying. You know this, right?
No. Yes.
So then, how do we proceed with nodal analysis? We need to add the currents at the node A. This is in phasor, so I need to look at this not as IX, but as I, capital I. So I'm going to add the currents at the node A and equate to 0. But we'll view these currents as voltage and resistance. You get that, right?
Yes.
Okay. So, how do we approach it? So let's take the currents at that node. First, we have IX. IX is leaving the node. So we're going to have minus IX, since it is leaving the node. Next, we have this source here, not source, this inductor there. Current through that inductor, we can take it that it is what? Leaving or entering? Which one do you prefer? Mostly, we always assume current is going towards the ground.
IX.
Pardon?
How did you get negative IX?
Because we are saying current is leaving the node and going down this way. That's why we are taking it as negative IX. It is leaving node A.
Then when you define the voltage that comes in the negative another way.
So instead of putting IX, I could have gone straight and say that to get current, remember, current is equals to what? Voltage over resistance. In this case, voltage over impedance, right? So the voltage here, voltage at its entry point is VA. Voltage where it is going to the ground, so that is 0. I might as well leave it out. So I'll have VA over the impedance. Impedance is minus J 0.1. This, by the way, is IX. Do you see that?
Yeah.
Next up, the J10 here. Again, we're assuming current is leaving that node going to the ground. So since it is leaving, we're going to take it as positive or negative?
Negative.
Negative. So can you express that in terms of voltage and impedance?
VA.
VA?
Over J.
Yes. Because it is going to the ground, you basically have minus 0. So no need to show that minus 0. Then you have that last part through the 1 ohm. Through the 1 ohm, we can assume, since we have a source here, we can assume current is coming from here. So it is going to be entering there. So we're going to have plus. Do you see that?
Yes.
So plus where it is coming from, you have VB. And remember, VB is the one we said, the one we positioned as the one supplied. So VB will be 1, phase minus 90. Then minus where it is going. Where it is going to VA, right?
Yes.
Then over the resistance there, which is 1. That is everything. So now we just have to simplify this expression. So how do we simplify this expression? So how will you simplify? J first can go up. For these terms where J is in the denominator, J can go up. Or first I can say this negative and this negative will make positive. So I have VA over J 0.1. Then this will still be minus VA J10. And then this side, I'll have plus. This will be 1. Phase minus 90 minus VA is equals to 0. Now, for these two, J can go up, right? Do you see that?
Yeah.
So when J goes up, now you're going to have J. We know when it goes up, it becomes negative. Then 0.1 divides into 1 to give us 10. Is that okay? Minus. For the second part here, J goes up, it becomes negative. So the negative will make this to be what? Positive. Then 10 divides into 1 to give us 0.1. Do you agree?
Yes.
Then this will still be 1, phase minus 90, then minus VA. So at this point, these two are like terms. So those two can easily add up. When they add up, what are we getting? Negative 9.9 VA. And then I'll say minus VA first, then plus 1, phase minus 90. Then I'll factor out VA. Well, I can take this first to the right side, and I'll have this minus 90. On the right side, this will be positive VA, then positive J, 9.9 VA. I'll rearrange and factor out VA. I'll have 1 plus J 9.9 is equals to 1 phase minus 90. Then I'll divide both sides by the coefficient of VA, giving me 1 phase minus 90 over 1 plus J 9.9. Have you seen that? Now at this point, it's a matter of how do you solve this. Again, we can choose to use the method we used earlier to say it's easier to divide when they are both in polar. So let's go polar. The maximum value can be obtained by getting the square root of x, which is 1, plus, not the square root, the square of x, which is 1, plus the square of 9.9. You remember this? What would be the value there? What's that?
9.95.
9.95.
Mhm.
9.95.
Yes.
So you did the square root of 1 squared plus 9.9 squared. That's what you did?
Yes.
Okay. 9.95. Then the phase angle, tan inverse of what? 9.9. 9.9 what? 9.9 over 1. Y over 1. Remember? So tan inverse of this will give you 84.2. Meaning our VA will be equal to 1 phase minus 90 over 9.95 phase 84. So now when we get the answer, the values, the magnitude part will divide and the angles will subtract. So I have 90 minus answer. We get negative 174. Right? Then the peak, we have 1 divided by 9.95. We get that. That seems to be very small. Perhaps we can keep it as this for now. This is in votes. I'm keeping it like this because this is not our final answer. Our final answer is Ix. We have found the node voltage VA. But how do we get Ix? Remember when we started, I did point out that Ix is this. Do you remember this?
Yeah.
So to get Ix, we just need to now divide the peak, the VA by that. So this is what we have. So how is it going to be? So to do this, we already have VA. VA, the minus comes, of course. VA is going to be, we're going to keep the minus down. We're going to have 1 divided by 9.95 phase minus 174.2. So we now want to express J 0.1 in polar as well. So what are we going to have? The magnitude part will obviously be 0.1. So we can look at it first as 0 plus the magnitude we have 0.1. And then we can put that minus there as well with the J. Even if we got Y to be all the way negative 0.1, you have to see that X is 0, meaning that the peak, I'll go with peak maybe being R cos phi, meaning R cos phi is 0. Since R is not 0 itself, why are we saying R is not 0? Because we know Y is equals to negative 0.1. X is 0, Y is that. So R can be obtained by X squared plus Y squared by Pythagoras theorem. Again, I think we did this earlier. So X is 0, Y is negative 0.1, notice that this will give you positive 0.1 as the peak. So if the peak is that value, then what must be the angle phi so that the value of z is just negative 0.01. So you want an angle such that, so you know y is equals to negative 0.1. So you want an angle phi that ensures that when you multiply it with 0.1, sine that angle, you should get negative 0.1. What this means is that sine phi has to be equals to negative 1. For sine to give you negative 1, the angle has to be 270 degrees or minus 90 degrees. We'll go with minus 90. Is that okay?
Yeah.
So the peak, we have seen the peak is 0.1. The angle is minus 90. So now let's divide. When you divide the peak values, so it will be that divided by 0.1, we get 1. So the peak value is coming out as 1.005. Then next, the angle. The angle we have minus 170. So that's minus 174.2. Then minus negative 90, so it will be plus 90. We get minus 84.2 amps. So this becomes our current Ix. So it looked like it was not going to end, but now we are concluding because we have found the value of phasor Ix in each case. So after finding these, we now have to add them so that we get our overall answer. So in this case, they are both in phasor form. So how do we combine them? So to combine them, we can even choose to take them to sinusoidal. So this one in sinusoidal waveform, it is going to be the peak 0.5546 cos angular frequency. This one, the angular frequency was 2t, then plus the phase angle. Let's take this whole lot. Because we know the overall value must be the sum of this and this. So the Ix now in time domain, I'll convert this one to time domain, which is going to be 0.5546 cos. For the first one, remember the angular frequency here was 2. The phase angle, we found 146.3. So we need to add this with the second one there. The peak value is 1.005. Then cos. So we have cos. The angular frequency for the second one, we have 10t. And then minus phase angle 84.2. So this is what we have. So this becomes the answer. So in this case, the two expressions are different based on this part. So we can just leave our answer in this form. So this becomes our final solution.